My name is Bob Harberts, and I am a system engineer with the Joint Polar Satellite System, or JPSS, at NASA's Goddard Space Flight Center. We begin with the Earth rotating about its axis. A gray-gridded plane projected through the equator serves as a reference. In this top-down view, we can see the distinction between day and night sides of the Earth, emphasized here with a yellow noon vector. The Suomi National Polar Orbiting Partnership Mission, or Suomi NPP, is the first satellite in the JPSS constellation. The orbit plane for JPSS is shown in orange. We can see how that orbit plane intersects the gray equatorial plane. The upward side of the orbit always crosses the equator at the same local time. This is called the local time of ascending node, or LTAN, which is measured from noon. In this case, the LTAN is 21.25 degrees from noon at 13:25 or 1:25 p.m. local time. This angle is fixed for JPSS orbits, so the satellite will always cross the equator at the same time. The angle between the plane of the equator and the orbit plane is called the orbit's inclination, which in this case is about 99 degrees. Together, these fixed angles define a sun-synchronous orbit. A sun-synchronous orbit means the orbit remains fixed with respect to the direction of the sun. In this split-screen view, we speed up the Earth's rotation to show 1 year of the Earth's orbit around the sun and how the JPSS orbit plane always stays oriented with respect to the sun. Satellites in sun-synchronous orbits always pass over the same location on Earth at the same local time, with the advantage of having consistent lighting conditions for observations. The second spacecraft in the series, called JPSS-1, will be launched and inserted in the same orbital plane as S-NPP. JPSS-1 will be placed 1/2 orbit ahead of S-NPP. This means the JPSS-1 will be about 50 minutes ahead of S-NPP in the same orbit, allowing important overlap in observational coverage. Now let's look at how the satellites observe the Earth. JPSS satellites have multiple instruments on board to observe the Earth environment and atmosphere. An imager collects data about the Earth's surface, depicted in green, and sounders that collect data on the atmosphere beneath the satellite is depicted in the blue triangular region. The trailing colors behind the satellite represent the data swath, or region where the data has been collected. As we zoom back out to include S-NPP, we can see how these data swaths overlap, providing better coverage. Even though the satellites are in the same orbit, they will fly over slightly different regions as the Earth rotates below the satellites. If we look at the entire imager data swath, we can see how the data builds up over time, covering the entire Earth. It takes about 14 passes for each satellite in this orbit to cover the entire Earth's surface. Now that the satellites have collected data, we need to send observational data back to Earth for processing and use. At this stage, the JPSS constellation uses 2 ground stations, Svalbard, Norway, near the North Pole, and McMurdo Station, Antarctica, near the South Pole. The yellow cones shown here represent the local field of view of the ground stations, which is approximately 5 degrees above the local horizon projected into space. As a satellite passes into the cone, we see a yellow line that represents radio contact and a downlink opportunity when the satellite is in view of the ground station antennas. Approximately 6-minute contacts are required to download stored data to the ground per pass. Notice that the ground station cone is not precisely at the pole, so the ground station appears to wobble, causing the contact opportunity times to vary slightly. S-NPP only contacts Svalbard, whereas JPSS-1 contacts both polar ground stations. For the next phase of the JPSS constellation, S-NPP is replaced by the JPSS-2 satellite and leads JPSS-1 by half an orbit. At this point, JPSS begins using NASA's Tracking Data Relay Satellites, or TDRS, in addition to Svalbard to downlink data. The TDRS satellites are in a geosynchronous orbit, which means they orbit at a rate that matches Earth's rotation. As a result, these satellites remain above the same location on the Earth at all times. The JPSS satellites can use these as a relay to send data down to the TDRS ground station at White Sands, New Mexico. In this view, blue lines depict when a TDRS satellite is in view of a JPSS satellite, and yellow lines indicate data downlinks to the TDRS ground station. While this visualization depicts all possible times data can be communicated to TDRS, operationally, only 6-minute contacts will be scheduled to downlink and relay data. JPSS missions will be joining an existing and future constellation of NOAA, NASA, and international satellites, including European, Japanese, and U.S. military satellites. These many missions vary in the orbits they fly, time of day observations they make, and Earth observing goals they will achieve. With this even larger fleet of satellites contributing to data collection, global space-based observational coverage of the Earth will happen even faster. Additional richness and value of constellation missions come from the collective sharing and use of data gained from them. Combining data from these satellites greatly improves global coverage, improves weather forecasting, and continues to increase our understanding of the Earth as a system.